Here we go. What we're going to learn about today is a little bit more about this idea of torque, right? In the last video, we learned how to calculate the torque produced by a force on a thing. We're going to touch on this idea of equilibrium, and then learn about the concept of what's called center of mass, with the ultimate goal of figuring out how to calculate the torque produced by gravity. All right, so the idea is, remember, gravity is a force, right? And forces have the potential to produce a torque. How do you calculate the torque produced by gravity? All right. Before I go on, a real quick comment that the notes here don't make any sense. It says the video is slightly different. The video is not different because why? Because this is the video. All right, here we go. So here's what I want you to imagine. So we've got this board, right? And the problem tells us it's a 20 kilogram board and it's 4 meters long, right? So let's go ahead and break the board up into 4 little chunks. Boop, boop, whoop. There we go, 4 meters, right? And the problem tells us it's 20 kilograms, all right? So our force of gravity on this thing is going to be 20 times 9.8, so 196 newtons, right? But the question is, where does it go, right? So technically what's happening is this board is made up of a bazillion molecules, and gravity is pulling them all down. So there's a little force of gravity here, and a little force of gravity here, and a little force of gravity here, and here, and here, and here. There's all these forces of gravity and all these different molecules, right, pulling it down. But that doesn't really help us, right? Because what we want to do is calculate torque, and to calculate torque, you have to do force times distance. So we need a distance. All right, and so in order to do that, what we're going to do is we're going to learn about what is called the center of mass. Okay, so let's erase this. Whoop. Oh, I erased my little 4 meter marks, didn't I? All right, so let's learn about this idea of center of mass. Okay, so where do we put our force of gravity on the object? Well, so the idea is center of mass is an object's average position of mass. If you average up the position of all those particles that make up that board, that average position gives you the center of mass. It's basically a weighted average, like you may have learned to do in your math class. All right? So probably the best way to see this is to use this little simulation that I've got here, all right? So what this little simulation here does is it allows us to figure out where the center of mass of a thing is, all right? So suppose we've got, I don't know, a meter stick. So a meter stick is long and skinny, right? And so because the meter stick is uniform, you can see that the center of mass is at the center, right? This little bullseye thing marks where the center of mass is, and you can see it's at the exact center of it, right? That's the average position of all of the masses, okay? Now, let's suppose that the top of this thing is heavier for some reason, right? Like maybe it's a T-square instead of a meter stick. It's shaped like that. So now what you can see is there's more mass at the top of the shape, right? Because the top of the T has more mass than the bottom of the T, and therefore my center of mass is higher up, right? Okay. Maybe your object isn't symmetrical. Maybe one side is heavier than the other. Oh, well then that moved my center of mass this way to the left, right? The center of mass doesn't need to be within the physical object, all right? So now, when we're solving problems, either I'll tell you where the center of mass is, or that's what you'll be looking for, and we'll learn how to figure out where the center of mass is mathematically, I think in the next video, okay? And a thing to note is this. So let's suppose that we've got, well, here, I'm going to get rid of this thing. Reset. Okay, so suppose we've got, I don't know, maybe a shape. Maybe it's just a long, skinny thing like this. Okay? All right? So right now it's sort of suspended in space. What I'm going to do is I'm going to take this little thumbtack and I'm going to stick it into the end over here. All right? Now when I click go up here at the top of the screen, you might not be able to see it, but there's a little go button up here in the upper left. When I click go, what it does is it sort of turns gravity on. Okay? Now remember, gravity is pulling down. All right, and what we're going to learn in a moment here in the video is that essentially you can treat the force of gravity as acting at that center of mass. So we've got a pivot point at the green thumbtack, and gravity is pulling down. So we've got a pivot point at the thumbtack, and gravity is pulling down at that bullseye. And what it's going to do is it's going to produce torque and cause this thing to rotate down, and it'll swing back and forth. I want you to notice when it stops swinging. So watch. Oops. Oh no, what happened? Oh, boo. Start again. Move the thumbtack. Go. Okay, so it's swinging, swinging. So in reality, it would swing forever, but there's obviously some friction there between the board and the thing. But notice it stops swinging when the center of gravity, the little bullseye thing, is directly below the support, right? Because what's happening is now gravity's pulling down on that little bullseye, and it doesn't produce any torque now, right? Because now my force is parallel to the lever arm, right? So it doesn't actually produce any torque. And so this is the way that you can find the center of mass of a thing, right? So suppose we've got some sort of really complicated object, right? Okay, and I want to figure out where the center of mass is, all right? Well, what I can do is I can take my thumbtack and put it in a spot, okay? And then what I would do is I would draw a line straight down. Let me see if I, there we go. So maybe I can draw, no, it's not going to let me do it. All right, whatever. But anyway, so what you could do is you could draw a line straight down from that thumbtack, and you'll notice it's going to go through my center of mass, right? Cool, so now I know my center of mass is somewhere on that line. So now what I can do is choose a new point and do it again, and now the center of mass is somewhere below there, right? Or I can, you know, put the thumbtack over here, right? And the idea is I'll have all these lines that cross, and the center of mass is on those lines. So where the lines cross shows where the center of mass is. Cool. All right, that's what I got for you. I hope that made sense. All right, so why do we care about the center of mass? Well, up until now, all of the objects that we've sort of considered the motion of have been point particles, right? Like when you throw a baseball, it follows this nice parabolic path, right? And so we're never sort of worried about the shape of an object, right? Like even when we did cars turning corners, we never worried about the car tipping over because a point particle can't tip over, right? But it turns out in real life, objects are not, always just a perfect point, right? And so it turns out, though, that if you follow the center of mass of an object, the center of mass is the one point that sort of it follows the path that a point particle would follow. All right, so I'm going to edit in a video that'll help you kind of see what I'm talking about here. It's easiest if you see it. All right, so here's that video. All right, so what this video illustrates is this idea that when an object isn't a point particle, when it's traveling through space, although individual points on the particle or individual points on the object might not follow sort of the laws of physics, the center of mass always does. All right, so check it out. So what's going to happen here is we've got this dude. He's going to throw a couple different objects, all right? It kind of speaks for itself. So here we go. So he's throwing a tennis racket, right? And you can see, oh yeah, it kind of like flips around and follows some weird path. So what they're going to do is he's going to throw it again, but this time he's going to focus just on the end of the handle, and watch, they trace the path out. And you can see that the end of the handle follows this weird path, which is weird, right? Because if we threw a baseball, it would just follow a nice parabolic path, right? It would just, whoop, So this time we're going to focus on the center of mass. Same throw, but this time there's the center of mass following that parabolic path that it would follow if it was, a baseball. All right? So that's the deal. Look, I'm in a new location. Better lighting? I don't know. All right. So anyway, so what does this whole idea of center of mass have to do with this board here, right? So the board is 4 meters long, right? So it's kind of like this, right? But you can see that the board is sitting on a support, and the support is only 0.75 meters. I'll have to rewrite that in a minute. 0.75 meters away from the edge of the board, right? So it's not in the middle. The middle would be 2 meters. So the support is boop, 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 over here, and if Roy doesn't touch it, it's going to tip over. So to prevent it from tipping over, Roy is going to push down here on the left side, producing a torque to prevent it from tipping clockwise, right? If Roy doesn't push it, it'll rotate clockwise until it hits the ground. To prevent that, he's going to push it, creating a counterclockwise torque to keep it from rotating, right? Okay, so Roy's torque counterclockwise, gravity's torque clockwise. Oops. Our goal is we want those two torques to cancel, okay? So let's see if we can make this happen here, all right? So I'm going to embiggen my board a little, or embiggen my drawing a little bit here. what forces are on this thing? Well, first of all, gravity, right? Well, the whole point of this video, if you only get one thing out of this video, is when you make your free body diagram, when you put your force of gravity on it, it goes at your center of mass. Now, what I didn't say here in the text of this problem that I should have said is I wanted this board to be a 20 kilogram uniform board. All right, so the word uniform simply means the center of mass is at the center. Okay, so like a meter stick is uniform as the center of mass at the center. A baseball bat is heavier at one end, right? And so your center of mass on a baseball bat is going to be closer to the heavy end because it's not uniform, right? That one end is thicker than the other. Okay, so either the problem will say the object is uniform, center of mass goes at the middle, or it's not uniform, and then either I'll tell you where the center of mass is, or that's what you're trying to figure out, which we'll learn how to do a little bit later on. All right, cool. So 20 kilogram board, 4 meters long, it's uniform. Boom, my center of mass goes right at the middle. That means my force of gravity goes right at the middle. 20 times 9.8, I think we did this before, is 196 newtons, all right? And then the other force that we've got is the force of Roy pushing down over here, right? Now notice, Roy's torque is going to be, counterclockwise, right? Although I guess I should point out a thing. In order to talk torque, we have to talk pivot point. Where's our pivot point? Well, at this point, I'm going to keep things simple. Let's just assume that the pivot point is right at that fulcrum, right? Because if it tips, that's the point that it's going to tip about, okay? In the next video, we're going to learn some other ways of thinking about that, but for now, it'll do, okay? All right, and so torque is, so I'm going to go ahead and label this with a P for pivot point. So torque is force times distance. How far is Roy's force from that pivot point? Well, the problem told us that it's 0.75 meters. All right, and then meanwhile, gravity's over here pulling down. Torque from gravity is clockwise, right? Because it's trying to make the board spin clockwise, right? Oops, I spelled clockwise wrong. Clockwise, there we go. All right, and how far is that? Well, the whole board is 4 meters, half of it is 2. So that means this distance is 2 minus 0.75, so 1.25 meters, right? Okay, so let's go over to here and find our torque of gravity. Oh my goodness, stupid tablet. So torque from gravity is force of gravity times distance for gravity. So the force of gravity is 196 newtons. The distance for gravity is this 1.25 meters, because that's how far the force is from our pivot point. That gives us 245 newton meters clockwise, right? So what that means then is, in order to prevent it from rotating, the torque from Roy has to be 245 newton meters counterclockwise, right? Okay, and what's the torque from Roy? Well, let's see, 245 newton meters equals the force of Roy, which is what we're looking for, times the distance from the pivot point, which is that 0.7, ooh, my goodness, 0.75 meters, right? Because, oh, you know what? I did this in the wrong color, didn't I? Blue. Oh, well, you people are just going to have to wait. I'm sorry. Change style. Blue. Done. There we go. Okay. So the force of Roy is 0.75 meters away from that pivot point, right? So here's the distance is that 0.75 meters. So now I just divide both sides by 0.75, and the force of Roy turns out to be 326.6 repeating newtons. Okay? And the idea is his distance is shorter than gravity, so he needs more force to compensate. Okay? All right, so there we go. So there's the force of Roy. So then finally, how much force is exerted by the support? Well, we know the board's not moving up or down at all, right? So this upwards force from the support has to be big enough to cancel the two downward forces. So what are the two downward forces? Well, we got 326 and 196. Add them up, and that gives you, what is that, 522.6 newtons. Basically just set it so that your net force is 0 because it is in equilibrium, which means it's not rotating or moving. Okay, more about this idea later on. At this point, if you understand this idea that you put your force of gravity at the center of mass, you're in good shape. All right, So, all right, one last example here. All right, so here we've got Thor's hammer, and you can see we're sort of trying poorly and not very effectively to balance it about this pivot point here, right? But because it's a hammer, the top end is much heavier, which means it is not uniform. And the little star here represents the center of gravity, the center of mass, okay? Ooh, if I haven't said this yet, I don't think I have. I've recorded this video so many times. And I'm hoping this final draft is good. Center of gravity and center of mass are, for all intents and purposes, the same thing, okay? Technically, if your object is really, really big, there's a small difference. But unless your object is galactically huge, well, not galactically, but, you know, Empire State Building sized, your center of mass and center of gravity are the same thing. So center of gravity equals center of mass. Oops, oh my goodness. Equals center of mass. Okay. Okay, so what we're trying to do here is we're trying to calculate the torque produced by gravity. Well, so this time the problem is my force of gravity pulls down. Notice where I put it at the center of mass. So the force of gravity is just going to be 80 times 9.8, so that's 784 newtons. All right, times my distance. Now my distance is the distance from my pivot point to where the force is applied. So my distance is the 0.4 meters. So remember, torque is force times distance times sine of theta. So for us, force of gravity times distance times sine of theta, where theta is the angle between the force and the lever arm. So this, the handle essentially is my lever arm. Here's my force. So the angle I want is actually this guy. So if this is 70 degrees, that means this must be 20 degrees. So to calculate the torque produced by the hammer, I'm going to do my force of gravity times the distance it is from the pivot point times the sine of the angle between the force and the distance, which is 20 degrees. So grab your calculator and you will get 286.3 Newton meters. And I guess on this one, it's going to rotate this way, which according to my math is counterclockwise. So there you go. So there's the torque. All right. I think that is it. Did I really not talk about, oh, right here, I did say it. Okay. Well, I at least wrote it. Maybe I didn't talk about it. All right. Cool. Center of gravity, center of mass, same thing. Have a good day.